Hello, this is Carolina. Science Architect can assist you in generating better and more easily testable scientific ideas and improve your overall creativity. It enhances your thought process and develops skill in finding new ways to apply scientific information in practice. In this video, I will demonstrate the essence of Science Architect by showing you the recommended workflow for analyzing scientific articles and the rules that need to be followed. While this video is a standalone tutorial, I still recommend watching two Science Architect instructional tutorials where I explain the functionality of how to use the information tree and how to model systems in diagrams. Firstly, it is essential to determine the scientific problem you are trying to solve or the scientific goal you are seeking to achieve. In this tutorial, I will focus on the problem-solution approach, but most of the principles will also apply to the goal-oriented approach. It is perfectly fine if the problem you are trying to solve changes over time. You can always create a new diagram with a new problem or a system of problems. In fact, this change is a part of the process, because during scientific knowledge analysis, you might find that another problem is more useful and more easy to solve. Science Architect will work if you do not have a particular problem or goal in mind. However, in this case, you should start analyzing scientific information with an intention to find a problem to solve or goal to achieve. To start, I will create two folders in the information tree, one for primitives and another for statements. In the primitives folder, I will add several classes. The first class I will create is Cancer, followed by a more specific class, Lung Cancer, and an even more specific class, Non-small cell lung cancer. Finally, I will also add breast cancer to the folder. Next, I will create a diagram. And add the component for cancer, lung cancer, non-small cell lung cancer, and breast cancer. Since these are the problems I want to solve, I will flag them accordingly. The relationship between these problems can be defined as follows. Cancer is more general and abstract problem compared to lung cancer and breast cancer, which means that there is a relationship between cancer and both lung cancer and breast cancer. To indicate this relationship, we need to use the inheritance relation, which is represented by a white triangle arrow pointing from the more specific problem to the more abstract problem. Finally, we can use the inheritance relation again to indicate that non-small cell lung cancer is a type of lung cancer. As you can see, I have created a system of problems to demonstrate the inheritance relation and how a system of problems can be constructed. However, in your case, you may start with only a single problem, and that is perfectly fine for beginning your analysis of scientific literature. As you progress through the process, you can add more problems to your system, and it will expand accordingly. You might ask, why do we need to have a problem? The idea is that analyzing scientific literature is not effective unless you have a problem you want to solve, or a goal you want to achieve. This approach helps you to think about how the information you find in articles relates to that problem. For example, does it help to solve the problem? Or does the information define the cause of the problem, and so on? By doing so, over time you develop the skill of constantly making connections between new information and already known information, and more importantly, identifying what problems new information could help to solve or what goals it could help to achieve. This skill can be very valuable across a variety of fields and industries. Once we have a problem or a system of problems, we can start analyzing scientific literature and extract related information. In this case, I would read articles and would look for information related to any of these problems. Before adding any components into information tree, you should know 4 rules. First rule, in the information tree, each component must be unique. For example, we must not have another cancer component in the information tree. However, components can be reused in multiple diagrams. In other words, I can have many diagrams and use the same component. This allows a single component to have many relations to other components through single or multiple diagrams. Second rule. The text in each component must be standalone, meaning it should be understandable without the presence of other components. To demonstrate that, I will open another project. If I remove all components in this diagram except this one, the information of the remaining component node must still be completely understandable without any redundant or unnecessary words. In other words, avoid creating copies of the same information in the information tree. Third rule. The text of each component should be as simple as possible. To learn how to simplify different types of components, visit the Science Architect website at sciencearchitect.com. Click on Documentation, Specification, Components. And find information about component types. Notice that some components have a prototype section which provides guidelines with examples on how a specific type of component can be simplified. Let's take a look at the statement prototype, which had several parts. Note that parts with an asterisk are optional. The statement of this prototype must include 2 things, A and B, where A does something to B. For example, antioxidants reduce the risk of cardiovascular failure, or radiation cause cancer. We can also define the environment of the statement, which provides information on the specific environment where the process of A doing something to B happens. For example, the antioxidants reduce the risk of cardiovascular failure in humans. The inhumans part of the statement defines the environment. Additionally, as the prototype indicates, we can define the state of the things mentioned in the statement. For instance, phosphorylated antioxidants reduce the risk of cardiovascular failure. The phosphorylated part defines the state of the antioxidants. Please note that the mentioned statements are only for example purposes and may not accurately reflect reality. You can also find other component types that have prototypes on this page, and you are welcome to explore them. In summary, try to keep the information in your components as simple as possible. The fourth rule of components is that the text in components should not be divisible. In other words, if the text of a single component can be divided into two or more components, then there should be two or more separate components. For example, if a sentence can be simplified and divided into two statements, each of these statements should be represented by a separate component. This means that each component should have a clear and distinct purpose, and its content should not be broken down further. Let's consider this sentence in the article. This sentence can be divided into separate parts. First part could be: EGFR mutations were observed in 42% of non-small cell lung cancers. And the second part could be: ALK translocations were observed in 6% of non-small cell lung cancers. You probably noticed that the initial sentence in the article allowed us to include more information into these two statements. I could add information about sequencing and other details. But for my current purposes, the information present in the components is sufficient, and I will not add what I do not need. As you might have noticed, once I find a statement of interest, for example, this one indicates that 4% of all newly diagnosed cases of breast cancer in the USA are due to alcohol use. I can add it into the information tree. If needed, I can also add reference information into that statement. In this way, all reference information will be easily accessible at any time. Once I have a statement in the information tree, I can add it into the diagram. Since the statement has information about the cause of breast cancer problem, I can indicate this by choosing a relation called positive and draw it from the statement to the problem. Notice that the target node, the node where the arrow points, is a problem. In summary, if a statement has information about the cause of your problem of interest, indicate it with a positive relation. I can also find the statement that indicates the solution or partial solution to the problem. For example, meat consumption reduced the risk of lung cancer. I will add it into the information tree and then drag it into the diagram. A relation that shows that statement indicates a solution to the problem is called negative. It has an arrow head with a minus sign in a circle. Interestingly, I found a statement that contradicts the one that was created previously. The heterocycle amines produced during the cooking of meat are carcinogens. Once I add the statement into the diagram, I can indicate this contradiction by using the contradiction relation. Also, we can indicate that this new statement has information that cause cancer problems. Because carcinogens that are mentioned in the statement cause cancer. Some statements might not indicate causation but only correlation. We have three relations that indicate this connection. First is a more general relation. It is simply called correlation and it is visualized by a dotted line. In contrast, a more specific relation is positive correlation, visualized by a dotted line with two white half arrows at both ends of relation. And finally, negative correlation, which is visualized by a dotted line with two black arrows at both ends of relation. As you might remember, I already added these two statements in the information tree. Interestingly, these statements indicate positive correlation between some genes and non-small cell lung cancer. I will add them into the diagram. And use positive correlation relation. For example, this statement indicates positive correlation because it states that mutations in this gene are frequently found in non-small cell lung cancer cases. During scientific literature analysis, we also might find some information that could help us to raise a hypothesis. This statement, almost 90% of patients diagnosed with lung cancer are cigarette smokers, could be used as an example. While it is a well-known fact that smoking contributes to lung cancer, let's assume that this information was not discovered yet and we just found this statement. In this scenario, it could help us raise a hypothesis. Cigarette smoking contributes to the cause of lung cancer. I can add this hypothesis into the diagram. And I can indicate that this statement could raise this hypothesis by using the rise relation. We can also indicate that this hypothesis has information that causes lung cancer by using positive relation. Now, by looking in this graph, we can easily identify the hypothesis due to its bright green color. Once we have a hypothesis, our next task is to use research methods to test its validity and determine whether it is accurate or not. As you might have noticed, Science Architect has many types of relations. In this tutorial, I have already shown several relations that are in large part sufficient to start modeling scientific knowledge systems. However, to find the meaning and use cases of other relations, you can visit sciencearchitect.com, go to Documentation, Specification, and press on Relations. You also might have noticed when we create a system of problems, we obtain a hierarchical structure in which the most general problem is at the top of the hierarchy. It's worth noting that the solution to this problem is also the solution to all other problems at the bottom of the hierarchy. For example, this sentence contains information that provides a partial solution to the general problem of cancer. I will add it to the information tree and will simplify it. Once the statement is in the diagram, I will use the negative relation to indicate a negative causation to the cancer problem. Important thing to note is that the cancer node here indicates a general problem. Therefore, the solution to this problem also applies to all subtypes of cancer that are shown in this diagram. In contrast, a solution to a lower level problem is only a solution to that specific problem and its children. Therefore, solutions to more general problems are more universal and have a higher impact, while solutions to more specific problems may not be as universal and have a smaller impact. However, solutions to more specific problems can often be more effective than universal solutions, although this is not always the case. Understanding the impact of solution, which can be easily observed through the diagram, can be important in prioritizing which problems to solve and determining what to focus on during literature analysis. I will provide some real-life examples that highlight the importance of concentrating on more general problems. The discoveries of RNA interference and genetic scissors called CRISPR-Cas9 are both powerful tools that allow for the targeting of specific genes. RNA interference allows for the silencing of any gene expression, making it universally applicable, while genetic scissors provides a universal way to edit the genome. These discoveries were recognized with Nobel Prizes, as they have the potential to address a wide range of issues, including the treatment of various diseases. They highlight the importance of focusing on general problems or goals during scientific literature analysis, and they can be easily identified in Science Architect diagrams. I would also like to note that the research methodologies used to achieve these discoveries were not necessarily more complex than those used for other discoveries. Rather, the most important factor is the ability to correctly identify and prioritize areas of research to explore. In other words, your aim is to formulate a hypothesis that has the potential to solve a problem that is as significant as possible by using as few resources as possible. This was a presentation of how to get started analyzing scientific literature with Science Architect in order to make great discoveries. I hope it was useful. Thank you for watching. Goodbye.